Thank you very much. Presentation is about blood damage modeling of FDA benchmark Nozzle. And before going through the presentation, I should acknowledge the work of Amanda Venegas, who was intern at our office, and great help and support from Andrew Span, my colleague at Veryst Engineering. I start with, I have 2 slides about our company, then I go through the presentation. In Veryst Engineering, we do engineering through the fundamentals. I am a part of multiphysics group of Veryst, but we also have a lab that we do different type of experiment. We do a lot of material testing and develop material finite element models. We do polymer mechanics. We have expert in microfluidics, additive manufacturing, failure analysis, and the list is long. I don't go over all of them. We are also a certified COMSOL consultant, and we provide training classes. I put here 3 examples from the work that we have done in multiphysics group of Veryst Engineering. The first one is LED cooling that involves CFD and heat transfer. The one in the middle is RF tissue ablation that involves electric field, tissue damage, CFD and heat transfer. And the one on the right is acoustic particle focusing that involves electric field, solid mechanics, acoustic, particle tracing, and CFD. Okay. I start this presentation by introducing hemolysis. Then I will discuss blood damage models. I will discuss about what is the effect of shear stress on red blood cells. I will show you the famous power law formulation, which is widely used to quantify blood damage. Then I'll show some experimental data, and we discuss blood damage history. Then in the last section, I show you simulation of FDA blood nozzle in COMSOL. I will spend most of my time on section 2, which is basically understanding the model and limitations of the model and experimental setup to develop those models. Once we understand that, given capabilities of COMSOL, implementing the equations in COMSOL is pretty straightforward. Okay, so what is hemolysis? Hemolysis is rupturing of red blood cells that release hemoglobin into surrounding fluid, which is basically blood plasma. The increase in hemoglobin could occur because some cells are ruptured, or there are many cells that are having leaks, incomplete leak through them. The concern of this study is mechanical hemolysis or shear-induced hemolysis, which happens in mechanical devices. So to wrap up this slide, if a red blood cell is damaged, hemoglobin is released, and by quantifying hemoglobin, release hemoglobin in blood, we can understand if red blood cells are damaged or not damaged. To encourage use of simulation for regulatory submission, FDA released benchmark case studies. One for CFD of blood analysis and prediction of hemolysis. There were two case studies. One was a nozzle, the other one was blood pump. The focus of this study is on the nozzle. CFD velocity profiles that were submitted to FDA generally match the experimental data, but among those submissions, only 1/3 tried to quantify blood damage. Okay, now with this background, let me go to the blood damage models that are used in CFD analysis. CFD blood damage models are either stress-based or strain-based, and they are either in Eulerian frame or Lagrangian frame. A stress-based model are models that local instantaneous hemolysis is assumed to be a direct function of local instantaneous shear. Strain-based models are models where local instantaneous hemolysis is not a direct function of local instantaneous shear, but there is another variable in between. For example, that variable could be extension of red blood cells. And as I said, the equations for red blood cell damage or release hemoglobin is in Eulerian and Lagrangian frame. It is easier to think in Lagrangian coordinate system because you can follow a red blood cell along its path line and predict how much hemoglobin these red blood cells release. And this approach is mostly used for steady flows where path lines are identical to streamlines. But the disadvantage for Lagrangian approach is that usually path lines start from the inlet, and there is a high chance that these path lines don't go to areas that have higher potential for blood damage. These areas include recirculation zones or next to the wall where the blood will experience high shears. One approach is to feed path lines inside the domain, but usually this approach is not sufficient. So usually Eulerian approach is more preferred. In the Eulerian approach, we solve transport of released hemoglobin. We solve transport equation of the released hemoglobin with the reference frame of the CFD solver. Okay. So, and shear stress are known to affect red blood cells and rupture them. If shear stress is higher than threshold value, if a shear stress that red blood cell is experiencing is higher than a threshold value, the red blood cell will immediately rupture. Grigioni in 2004, he did a literature summary of all the threshold shear stress threshold value which are reported in literature, and I put it here for record. But if shear stress is not above that threshold value, then shear stress can cause forming pores on the red blood cell when a stress strain exceeds a critical value. So with this background, now let me go to the formulation for the blood damage. In this presentation, we are investigating a stress-based hemolysis model. And these models comes from fitting experimental data measured in a viscometer. The model is here. H on the left-hand side is the amount of released hemoglobin in the blood, which is a function of tau, which is a scalar that measures stress on the red blood cells, and T, which is the amount of time that red blood cells experience that stress. This model is called power law, and it was first proposed by Gersipian in 1990, and it has been very popular and has been widely used. But the underlying assumption is that the stress is measured in a viscometer where constant shear is applied on the load. In this model, C, alpha, and beta are constant, which are basically obtained from fitting this curve to the experimental data. Now, there are several variations of these models, and several values for C alpha and beta are proposed. Different values of C alpha and beta are proposed by different groups that are in this table. But as I said, the underlying assumption in this model is that red blood cells are submitted to shear stress, which is constant in time. So these models are applicable as long as this assumption is met, which is shear is constant and usually not too high, and the exposure time is usually short or intermediate. It is less than 1 second. Now, what are the limitations of this model? The power law model that I showed is the basis model for blood damage estimation, but it has many limitations. One is that the mechanical load, which is applied on cells when blood goes through an artificial device, is significantly different than a mechanical load which is applied on cell during well-defined and controlled stress condition in a viscometer. In this model, equation relies only on one value for shear, whereas deformation and shearing of red blood cell is caused by shear tensor, not just one value of shear. And red blood cells experience different mode shapes. For example, they may shear, they may elongate, and shear and elongation will have different effect on the cells. None of this is captured in the model. The other thing is that it is assumed that cells respond instantaneously to the shear, whereas cell is a flexible material, red blood cell is a flexible material, and it has its own time scale. And the most important thing is that shear stress and exposure time are not independent variables. You can apply high stress to a cell for a short time and the red blood cells will survive that stress. But if you apply low stress for a long time, that red blood cell may start to leak. Given all these limitations, you can assume that developing experiment that can capture all these requirements is extremely challenging, and that's the difficulty that we are facing when we try to model blood damage. In 2017, you published a paper, which is a very interesting paper. He compared different models, different stress-based and strain-based model, with an experiment that he did where he applied constant shear to the blood. So the experimental setup is basically satisfy the requirements of this model where constant shear is applied to the blood. The horizontal axis of this figure is the shear rate which he applied in the model, and the vertical axis is blood damage index, and it's in logarithmic scale. The gray curve is the experimental data, and these colored bars are all experimental data. One you can see is that different models are predicting different results, and there are even like 10 orders of magnitude difference between predictions between different models. And even some models are predicting an index which is higher than 1 that cannot be true. So lack of well-documented experimental data suitable for validating the models is a challenge in this field. Among the models, one model is doing relatively good job. This is a model proposed by Grigioni, which I will discuss it in the next slide. And I use that model to quantify blood damage in the nozzle. With a couple of simple examples, Grigioni in 2004 showed that the power law model lacks sensitivity to the cumulative effect of previously applied stress magnitude. What does it mean? It means that if you consider two red blood cells and they experience different stresses as they move, and now at current time they have, if you apply same stress for the same time on them, the power law predicts that the same amount of hemoglobin is released, whereas in reality these two cells, because they have different history, they should respond differently to the same stress. This is not captured in the power law model. So in 2005, Grigioni proposed another model that accounts for the blood damage, and he mentioned that a good model should have 3 requirements. First, the good model must reproduce power law when uniform shear stress is applied. That makes sense. The model must not clash with the principle of causality, and explain what it means here. So let me refresh your memory. In the power law model, H is the amount of hemoglobin that is released, tau is the stress, and T is time. If you do chain rule, then DH would be a function of D stress. And if a stress is changing in time, and if d tau is negative, meaning that if a stress decreases, power law formulation predict that dH, amount of released hemoglobin, will decrease, which is not physical. Released hemoglobin cannot come back to the red blood cell. So this is the second requirement. And the last requirement is that the model should account for load history. I explained that. It means that two red blood cells that sustained the same stress before should respond differently now if same stress is applied on them. Okay. So Grigoni introduced mechanical dose D, where the mechanical dose accounts for the history of loads which is applied on the red blood cells. Basically, the differential dose experienced by cell over a given time dt is dd, which is this function of stress, and alpha and beta, which are coming from this commutator test. I won't go through the equation. You in 2017 provided the equation that Grigoni provided in Lagrangian frame in Eulerian frame, which is these two equations. So let me elaborate on these two equations and how to solve about them. Let's say if you want to use these two equations. First, you solve background flow to predict velocity flow and blood velocity everywhere in the domain. Then you solve this advection equation for the mechanical dose, where V is the velocity and tau is shear stress. You have it from the first solver that you put, which you get velocity of the flow, and you can get shear stress everywhere in the flow. So you solve this equation, you get mechanical dose, distribution of mechanical dose. Then you go to the next equation. H is the amount of hemoglobin that is released. V is the velocity which is known. Beta, alpha, and C are the parameters from experimental data, and D is the mechanical dose that you solve in this model. So you can solve now you can solve H, which is the amount of released hemoglobin. I should add that in the paper that's published by you in 2017, there was a mistake in driving this equation. It was a minor mistake, but there was a mistake, and he solved wrong equations. These are the right equations to solve. Okay. The only issue here is that these two equations that we have to solve, these are pure advection equations which are unstable to solve. So we need to add artificial diffusion to the model to solve it. And this artificial diffusion, of course, should be small so that it will not affect and it will not pollute our solution. Okay, I finished this section with reading a couple of quotations and a conclusion. Shima said that the concept of universal theoretical blood damage model clashes with the complexity of the involved problem. Grigoni said that to date, universally applicable blood damage models have been proven to be elusive. And Yeltsin said that attempts were made to provide an analytical formulation, but the drawback of these theoretical approaches is they need several empirically calibrated coefficients. And the conclusion is that we need, in order to quantify blood damage, we need well-defined, reproducible, and well-documented experiments that have higher generality and accuracy. These experiments should account for time-varying shear stress, and this is very important. In this experiment, blood samples should be exposed to different flowable conditions to identify calibrated coefficients for a class of flow field associated with a certain artificial organ. In other words, we cannot just use flow in a viscometer to predict blood damage for any type of flow. The physics just do not match. For different types of flow, we have to do different set of tests, and each test should be calibrated. Each set of tests should be calibrated individually, and these experiments should account for time-varying shear stress. Okay, now let me go to the nozzle case. So, as I mentioned before, we have to solve this equation, these two equations to quantify blood damage. Before that, we need to solve blood flow in the nozzle. I use SSD turbulence model to solve the background flow. Then I use Eulerian and Lagrangian approaches to quantify blood damage. The model that we use is 2D axisymmetric model. In order to implement them in Eulerian, in order to solve them with an Eulerian coordinate system, we use transport of dilute species of COMSOL, where the right-hand side of these equations are reaction terms. And for Lagrangian implementation, we use auxiliary dependent feature of particle tracing in COMSOL, where differential equations are solved along the path line. Okay. And the blood that I use for the model is I assume it's a non-Newtonian fluid because its shear stress is high, and density is close to the density of water, and viscosity is 3.5 centipoles. This figure shows localized stress, localized rates of blood damage. The flow is moving from right to left. So the simulation predicts that most of blood damage is occurring right here. And the immediate solution is most probably to reduce the slope here. Then you will reduce the shear and you will get less blood damage here. We got same result when we used Lagrangian approach. Here I am plotting the path lines that have higher contribution to the blood damage. You can see the path lines are path lines that are next to the wall, and blood damage start to increase significantly right here where shear stress increases. Okay, now let's look at experimental data. So 23 labs performed experimental data on blood nozzle, and they submitted 27 results. This figure, each of these bars correspond to the measurements done by one lab, and the black bar here is the average of these data. The bars in the middle correspond to the case which is called gradual cone, where flow is moving from left to right, and flow rate is 6 liters per minute. It is interesting to see that for this case, the blood damage which is measured by these three labs is not significantly different from zero, and some of them predicted negative blood damage, which is wrong. As I said, the average is not significantly different from zero, and our simulation is this dotted line that do not match the experimental results. Now let's look at when flow is moving from left to right, which is called sudden contraction. Experimental data is done for 5 liters per minute and 6 liters per minute. And the black line here is the average of these experimental data. The dotted line is our simulation. So as you can see, when flow rate increased from 5 liters per minute to 6 liters per minute, blood damage, experimental blood damage suddenly increases, as if there's a tipping point here. Our simulation cannot capture this sudden increase in blood damage. And even our simulation cannot sudden increase in blood damage when we go from gradual cone to sudden contraction. None of this is damaged. None of this is predicted by our simulation. Now, it's interesting to see that we see this tipping point or sudden increase in blood damage in the other benchmark tests that FDA released. FDA released also a benchmark for pump, where again different lab provided their results, and this is the summary of results. vertical axis is a representation of blood damage or released hemoglobin, and horizontal axis is different pump condition. Condition 6 is the condition that blood flow rate increases to 7 liters per minute. So what you see here is that, again, there's a tipping point. Blood damage suddenly increases when flow rate increases from 6 to 7. We see this increase in blood damage. We see this increase in we see this tipping point and sudden increase in blood damage. Also in the nozzle case, when flow rate increased from 5 to 6. Simulation and power law simulation cannot capture tipping point. This sudden increase cannot captured by power law equations. So let me see how much time do we have. Okay, it's 3. I go to my summary and conclusion. For summary, we use Eulerian Lagrangian approaches to obtain blood damage. A stress-based power law model cannot capture this tipping point behavior, where further increase in flow rate increases hemolysis significantly. Hemolysis models are useful to say that which geometry is good, or for ranking geometries when there's a slight modification in geometry. They cannot predict absolute blood damage. They can be used just to rank design. And we should always remember that the correlation used for hemolysis models are developed for shear dominated flows. Finally, Nick Ware in 2020 proposed a model which might be captured this tipping point. This model is a multi-scale model, and it would be very expensive to run, but it has the potential to capture that, where basically history of red blood cells is captured in the CFD model. Then the result is passed to another model where simulation is done over a red blood cell.